Hey there, folks. Back here with another video. I hope I'm almost done wrapping this up. What we did last video is we introduced the fundamental theorem of calculus, and we had introduced ourselves to a technique through part 2 of that theorem to calculate to make our lives easier calculating the definite integral. And what I want to do in this video here is I want to come back to some of those properties that we've seen with regards to the definite integral and look at a little bit more application of those properties in the calculation of these net areas using this fundamental theorem of calculus part 2 to help us out in our calculations, right? To kind of, in a sense, give us a little bit more example to go with here. All right, let me bring up my notes. Where's this at? Right here. Again, just to summarize, we've made a connection to several ideas here, folks, if you take note. In summary, for a function over some values of x in the interval from a to b, the net area trapped by f over this interval, right? This net area was given by that limit of the Riemann sum, which we noted was also defined by what we call the definite integral of our function from a to b, where we were able to see that definite integrals calculation was essentially related to the antiderivative of f given by cap f here, where cap f, when evaluating the definite integral, can be used by evaluating cap f at b and taking away from it cap f at a, and that difference leading to the value of our net area. All right. We developed over the last few sections of our study this idea of net area being this limit of the Riemann sum and being this definite integral that can be calculated with our antiderivative, as seen here. All right. But I want to practice that a little bit more. But at the same time, I also want to take note on some useful properties. If you remember back, I think it was back in the definite integral section of notes, we quickly ran through some properties, but we didn't spend a lot of time here with these because they're kind of hard to see. They are difficult to present back there in that section because we really hadn't learned yet a technique for calculating that definite integral. Right? Whereas here in this case, right, if we go back and we consider some of these properties, right, here I think we have 5 of them all together, so I'll bring all 5 up in the picture. All right, these are the 5 that we're going to go back and look at today, or actually I think 4 of these 5. This first one I'll just make comment on. Just take note, remember the first property here says that if we reverse the orders of our integration, if we, instead of going from a to b, we go from b to a, right? B still being larger than a in value, the value we're going to obtain is actually going to be the opposite of what we would have if we went from a to b. All right? Reversing that order will give you the opposite value in your integration. And we can actually back up and see that here. Reversing this order of a and b will actually produce f of a minus f of b as opposed to f of b minus f of a. And we note changing the order of a difference will produce the opposite value. And that's what we see happening here in this first statement theoretically. All right. Now what we've also seen is that the derivative operator will distribute itself across sums and differences. That if we have a constant multiple times a function, the constant multiple will factor itself out of that function, right? An integral from a to b can be broken into 2 separate summations of integrations from a to p and from p to b, right? If p, well, and really p doesn't have to be in between a and b. This can be for any values of a, b, and p. All right. And lastly, if we take the absolute values derivative for a function, it is actually going to be the sum of the net areas for when the function is greater than 0 minus the sum of the net areas for when the function is less than 0. right? In other words, it's going to be all the physical area trapped by our function, neglecting or ignoring direction of that net area. All right, it's the sum of I should be careful there. It's the difference for the net area for the regions above the x-axis with the net area for the regions below the x-axis. All right, it's going to be the difference of those quantities, because the areas below are going to be minus or negative in value. When we minus those away, they'll turn back to positive, and we'll actually get a physical area. That's that absolute value effect. Now let me look at these with some example. I'll give a couple of examples here to highlight these properties. This first example considers the net area trapped by this curve, 5x minus 3x squared. This curve seen here over values of x from -2 to 3. Over this interval from here, -2 to 3 along our x-axis. We can see this is the net area that we have trapped here. Some of this forming below the x-axis, some forming above. Well, if we go ahead and calculate this using the rules that we've defined, right, from the fundamental theorem of calculus, we know that that definite integral calculation will be the antiderivative function evaluated from -2 to 3. It'll be the value of the antiderivative at 3 minus the antiderivative at -2. Well, in this case, our antiderivative, if we apply the antiderivative rules to the statement 5x minus 3x squared, will actually become 5/2 x squared minus x cubed, plus some constant value. So in our calculation, if we just ignore the constant within our antiderivative, because it is going to cancel away anyway in the definite integrals calculation, substituting that antiderivative into our statement here for cap f of x, and then evaluating it across these bounds, taking its value at 3 and taking away from its value at -2, when we perform that math, we do find it equals -45/2 in value. All right, this result seen here. That is just calculating it with purely the fundamental theorem of calculus, part 2. Where we now know that value from that methodology, but let's compare it to some of the results we get from the properties above. For example, if we consider using properties 2 and 3 of definite integrals, all right, that definite integral operator, let's see, that's it, will distribute itself across this difference, and those constant multiples of 5 and -3 will factor themselves out, and you'll have 5 times the integral of just x from -2 to 3 minus 3 times the integral of x squared from -2 to 3. Where we will have x's antiderivative become 1/2 x squared, which will be evaluated from -2 to 3 and times 5. And we will have x squared's antiderivative, which is 1/3 x cubed, evaluated from -2 to 3 times that constant multiple of -3 out in front. And if we evaluate across those bounds, right, between -2 and 3 for 1/2 x squared, we will get 9/2 minus 2, which is 5.5. Right? And if we evaluate 1/3 x cubed across the bounds from -2 to 3, we'll get 9 plus 8/3, which is 35/3. If you, again, go common denominator with these sums and differences. Right? Where when multiplied by -3, 5 times the 5/2 and -3 times the 35/3, we get -25/2 minus 35, which again simplifies to -45/2. Right? The value that we obtained by just using the fundamental theorem of calculus above. Right? Here, highlighting properties 2 and 3 in our calculation. That distribution property, where we distribute across the difference here, and then that constant multiple property factoring out the 5 and the 3. really just evaluating the powers of x and x squared's derivative in the antiderivative calculation. All right. Let's look at one other property here in this example. Finally, if we take note from property 4, bring this into view. From property 4, we can actually divide this integration into any two or more integrals summed together if we break it apart across, right, at some common value of p. And here we chose a common value of p equal to 1. So we integrated from -2 to 1 this function 5x minus 3x squared, and we evaluated from 1 to 3. -2 to 1 and from 1 to 3, covering that entire interval from -2 to 3 in value. And if we calculate these definite integrals alone, individually, right, from the fundamental theorem of calculus and applying it along the way here, we will end up with -18 minus 9/2 in this case, which when we simplify again, will yield -45/2. The exact same result we had obtained in the previous 3 examples. This case, though, illustrating property 4, where we take our single integral and divide it into the sum of 2 separate integrals by using a common lower and upper bound where the 2 integrals separate themselves. All right. All right, let me show you another example here, folks. The absolute value example. Let's consider the definite integral for the absolute value of 4 minus x squared, all integrated from 0 to 5. What we're calculating in the case for absolute value, right? Remember, the net area for the absolute value of 4 minus x squared is actually going to be the difference between the positive net areas trapped by f over that interval from 0 to 5 and the negative net areas trapped by f over that interval from 0 to 5. All right. We're going to take the difference between the positive net areas and the negative net areas. It's going to, in a sense, be the physical area of the space we are calculating the net area for, trapped by the function without the absolute value in the calculation. All right. For just function f alone, not for the absolute value of f of x. All right. Now, if we think about that situation, in other words, what we're going to be calculating here is the net area trapped by the absolute value of 4 minus x squared, which would actually be the portion, right, of the shaded area trapped by this function seen here, where what used to fall below the x-axis in just 4 minus x squared now reflects back above because the absolute value forces it to be positive. So what we end up having to calculate here is the net area from here to here, which is going to be an entirely positive value, which is going to include this positive net area and this space here, which is actually the opposite of this negative net area. It's going to be the minus that negative value in our calculation. That's what we're calculating here. Right? And what we do notice is that negative net area formed by f in that interval, right, has been reflected above the x-axis in the case for the absolute value of f. It's this space that's been reflected up here. So the net area for the absolute value of f is actually going to calculate the physical area trapped by just the curve f itself. All right. So what we have to do in this case is we actually have to break it into 2 integrals. One that calculates the area for the positive space that happens from 0 to 2, And then the other integral that calculates the case for the negative space from 2 to 5 in our calculation. And we have to find the difference of those two definite integrals. So for the absolute value of 4 minus x squared, the graph seen here trapping just the blue region of space, right, all above my x-axis, we do calculate the area from 0 to 2 for 4 minus x squared, and then calculate the net area from 2 to 5 for 4 minus x squared, but we take it away from the previous result. It's a minus in the case of the absolute value. In a sense, you're calculating two separate areas. If you think about applying this difference here, you're actually taking the sum of the positive for what's going to be the opposite of this function. And what's the opposite of this function? Well, the opposite of this function is x squared minus 4. So you're actually calculating the net area trapped between two different functions, one function and its opposite, over two different regions here. The original function from 0 to 2, because that's where we see the positive area, and the opposite function from 2 to 5, because that's where we had the negative area. Now let me undo all that if I can. Get there. Right? That's what that minus is having the effect of. Now, if we calculate each of these antiderivatives, 4 minus x squared's antiderivative is 4x minus 1/3 x cubed. And if we evaluate that across the bounds from 0 to 2 and from 2 to 5, we get these results seen here and here, which the first result simplifies to 16/3, and the second result simplifies to negative 65/3 plus 16/3. I'm going to be careful here. I need to grab, I think that difference needs to distribute across that entire quantity there. To get that 16, no, it wasn't going to cancel. Oh, because that's going to be a minus anyway. Yeah. Okay. Yeah, so that we already distributed this negative to this fraction and to this fraction to make that fraction positive. So we end up with 97/3 as the physical area of space trapped by the function 4 minus x squared, or what would be the net area for the absolute value of 4 minus x squared. All right. That would be 97/3. I do think I just conclude that result here. Thus, the net area described by the absolute value function is 97/3. And that's the physical area of space trapped by just the function minus the without the absolute values, right? With the absolute value symbols removed. All right. Now, in addition to those properties, there are two other properties this section presents as new. And this is what's called the even and odd function property of integration. And essentially, we can exploit the shape of symmetry in our integrals if we're integrating across a symmetrical region that corresponds to that symmetry. All right. For example, if f of x is an even function, and we integrate from negative a to a across that function f of x dx, since it is even, it's going to exploit that symmetry and consider just the definite integral for 2 times the definite integral across the boundaries from 0 to a for our function f of x dx. Because to the left and to the right of 0, down to negative a and up to positive a, the graph is going to have this y-axis symmetry, this similar appearance on either side, a mirror image across that y-axis. What you find underneath one of them from 0 to a is the same as what you would find on the other half. So just doubling the 1/2 from 0 to a is going to be enough to calculate the entire area from negative a to positive. Whereas for odd functions, if you go from negative a to positive a, and you have an odd function, what will happen is the areas will cancel. in terms of net area. The positive region will have the same size as the negative region due to the symmetry, and those values will cancel. Here's a couple of examples. Right? You do have to have opposite boundaries for this theorem to be applicable. So here we might consider the definite integral for x cubed minus 4x across the boundaries from -1 to 1. Well, going from -1 to 1, having opposite boundaries, I'm going to go ahead and look at the even or oddness of this function. And what I can point out is that this is an odd function. And I can see that with a little bit of algebra. If I substitute in negative x into the function, that does become the opposite of f of x. That means it's odd. Remember, f of negative x, if it equals the opposite of f of x, you have an odd function. And that is the case here for this f of x, which equals x cubed minus 4x. So what does that mean across the definite integral across these opposite boundaries? Well, that's going to imply that that value is equal to 0. All right. Yeah, that will just be equal to 0 in value if we were to calculate it. And if we do go about evaluating it by hand using the fundamental theorem of calculus, we will be using the antiderivative of x cubed minus 4x, which is 1/4 x to the 4th minus 2x squared, where when evaluated across those boundaries produces the same result. And the difference of those two common results is nothing more than 0, confirming what we had said earlier from the result for from the theorem for an odd function. And notice the graph. Here's our function, and we are integrating from -1 to 1, where you can see these, because of the odd symmetry, these two regions are the same size but on opposite sides of the x-axis, so they cancel with each other in a net area calculation. All right, let's look at one more example here. What about for the even function x to the 4th minus 9x squared? If we evaluated it across the bounds from -2 to 2 for its definite integral, right, we should be able to, because that's an even function, be able to exploit its symmetry. Now, how do I know it's even? I notice if I substitute in negative x into the function, the negative x gets canceled and becomes just f at x. Right? It has 0 effect. The function can be simplified back into the original function if negative x is substituted in. That's what becomes an even, well, that's what indicates it's an even function algebraically. So that means the integral I want here from -2 to 2 is just twice the integral from 0 to 2. And we can set that up. This definite integral from -2 to 2 is just twice the integral from 0 to 2 for our function. Our function's antiderivative is 1/5 x to the 5th minus x cubed for the quantity x to the 4th minus 9x squared. So if I evaluate that from 0 to 2, that will all evaluate to -88/5, where when I double that, I'll have -176/5. That would become the value of that definite integral, exploiting its symmetry. Now, if I was just to evaluate using the regular bounds from -2 to 2, my antiderivative would be the same, and then across those boundaries, what you would see is I'd inevitably be adding up the exact same value 2 times. That value being -88/5. The value from 0 to 2 would be added to itself 2 times here, which would yield -176/5 again. All right? Again, confirming the result given from the case of an even functions integral across opposite boundaries. What we see happening, we can see here in the graph, the integral from -2 to 2, because of the symmetry, is just twice the integral from 0 to 2. Because of the symmetry, these regions have the same size on either side of 0. Between -2 and 0 and between 0 and 2, these regions are the exact same size. Right? So we can just find the definite integral for one of those regions to find its net area and then double it in the calculation. And that's what I had done initially. I found this net area and then just doubled it to include this one. And in the end, produced -176 of a unit squared was my net area. All right, folks. These are just some properties and more examples of working with the fundamental theorem of calculus and definite integral calculations and how it all relates to net area. We did present ourselves with two new ideas here in the second theorem for even and odd functions. I will caution you, though, this only works in very specific cases where your boundaries are opposite in value, whereas the properties we introduced initially work in every case of a function, right, across any boundary in the calculation. Right? We don't need to work with opposite boundaries in with these properties. All right. So again, that's just a little bit more review of net area, kind of a bit of a summary of what is net area and its calculation now using the fundamental theorem of calculus. And in the process of going through some more example with that, also exploring some of the properties of definite integrals. All right. At the moment, I got just a few more videos I hope to put together for you this semester, folks. In the next one, we're going to talk a little bit about the average value of a function. It's a quick video, and it'll introduce mean value theorem. And I know I will need to do a video on what is called U substitution, kind of an advanced integration technique. The first of a few advanced integration techniques, and I will introduce you to that before the end of the semester here. So, and then there might be one or two other videos I include just at the end for material we either want to discuss in class if we have the time, or if not, at least have in addition to what we have presented so far this semester. All right. So with that said, I'm going to end this video, try to keep it under half an hour, and I will be back in the next one, where the next one again will be quick, and then we have U substitution, which is going to take a little bit of time to develop. But I'll see you in those next ones, folks, and I'll end this one here.